we're going to talk about circular motion, and particularly the forces involved in circular motion for something like a satellite orbiting a planet. But before we can really understand circular motion, we've got to deal with the bogeyman of circular motion. And the bogeyman of circular motion is centrifugal force. This is this outwards force that pushes you away from the center of the circle. So you turn to the right in the car. It's the force that causes you to slam against the left-hand side of the car. Well, the thing about the centrifugal force is that it doesn't exist. It is not a force. It's a fictitious force. Now you might say, aha, I know what it's called. It's called the centripetal force, and centripetal is just another name for centrifugal force. Well, it's not at all. Centripetal force is a real force. That is the force that causes you to go in a circle. Centrifugal force is an illusion. Let's have a look at the situation whereby this illusion might come about. So we're driving in our car and we're going to turn our wheels. Now let's imagine turn our wheels to the right here. So those tyres are then going to push outwards on the road, and the road's going to react and push in the opposite direction on the car. That's Newton's third law. For every action there's an equal and opposite reaction. And that creates a force towards the centre of the circle that causes the car to accelerate in that direction. Aha, but you're saying what happens is then the centrifugal force comes into play and pushes you outwards against the wall of the car. Well, that's not the case at all. And to understand it, it's best if we take a bigger, broader view and step back a little bit and look at it from a higher point. So here we are in our car, and the friction force between the tyres and the road are creating the centripetal force, which is causing our car to accelerate around the circle. Because if that wasn't there, according to Newton's first law, the car would just continue on in a straight line. Well, the car body would if it's not connected to the wheels. And of course, you would continue along in a straight line too if there wasn't a force on you. But remember, there is no force on you because the force is on the car. So somehow the car has to apply that force to you. Well, what happens is you keep going in a straight line and the car, as it were, accelerates in towards you until you're contacted with the seat belt or the belt or the seat or some way for the car to put a force on you to accelerate you towards the inside of that circle. So the only force that is acting upon you is a centripetal force. Yes, you're pushing against the door of the car. That's a real force, but that's not a force on you. That's a force on the car, okay? The force is on you. The only force on you is a centripetal force. If there was an outwards force, another force to balance this force here, so if those two forces were balanced, if that was, as it were, the centrifugal force, then what would happen? You would go in a straight line because the forces are in balance. But you don't go in a straight line. You go in a circle, and the reason that you go in a circle is because you're accelerating because there's an unbalanced force upon you. Okay, so let's consider the situation of a satellite in orbit around a planet. For it to go in a circular motion, there has to be a centripetal force. And that force we can define, if you remember back to prelim course, we can define how big that centripetal force has to be. Well, it was Newton's genius to realise that the centripetal force is actually supplied by gravity. This universal law of gravitation, that any two objects, this is mass 1 and this is mass 2, any two objects with mass just create this force between them, this attraction between them, this weight force between them. And so it was Newton who realised that things go in a circular motion because there is a force causing them to do that, to stop just travelling in a straight line, and that force is this universal gravitation. The same force that causes an apple to fall to the ground is the same force that causes a satellite to fall to the ground, except the satellite has got a horizontal velocity, so it's always falling over the horizon, as it were. Okay, that all makes pretty good sense. Then why do astronauts in something like the space station, why do they appear to be weightless if there is this weight force that's causing them to accelerate? Why isn't it like the car? Why aren't they slammed against the outer wall of the spacecraft as it goes around? Well, the reason that happened in the car is because the car had to provide the centripetal force on the person. But remember, you're an object with mass in a gravitational field as well. So there's going to be a centripetal force on you and a centripetal force on the space station or whatever it is that you're in. So both of you have the same centripetal force. Are you accelerating? Yes, you are, because your velocity is changing. So you're both accelerating at the same rate in a gravitational field. And so there is no force between you and the spacecraft. And so you appear to be floating around in that frame of reference as though you are weightless. But of course you are very much weighted. You have weight. That is what's causing you and the spacecraft to travel in a circle. And so it's like you're in free fall in an elevator, except you're constantly, as it were, falling over the horizon. So the forces involved in circular motion are very simple. There is a centripetal force, otherwise it doesn't go in a circle. And when we're talking about satellites around planets, then that centripetal force is provided for by Newton's law of universal gravitation.